Well, we finally have reached chapter 12, and for the first time in Calc 3, we will actually start to do some calculus. Now, if we want to be able to do some calculus, some derivatives, integration, etc., then we need functions to take derivatives of. So let's recap really quickly. Now, normally, the types of functions that you have been introduced to are functions such as, say, f of x. An example would be something like f of x is equal to 2x plus 1. Now, structurally, what's happening here, okay, as with all functions, you have an input, right? In this case, the x would be your domain, right? Now, it's possible there are restrictions to your domain. In the example that I've given, 2x plus 1, there are no restrictions. We don't have to worry about division by 0, square roots of negatives, things of this sort. So the domain includes all real numbers. So again, structurally, what exists in this set is all real numbers. All right, now, the idea of a function is you can think of it as a machine, right? It's a machine of transformation. So that what we're doing is we have inputs from one set are being mapped to outputs of another set. Let's just do one. So for example, f of 1, right? We know that that is just simply 2 times 1 plus 1. In other words, f of 1 is equal to 3. Now back to our sets. So somewhere within the circle would exist the real number 1. And the idea is we are transforming, we are mapping 1 to 3. Right? And we refer to this second set, this output set, as the range. All right, so all that we need to know, structurally, is you can't get a 1 to become a 3 unless it undergoes some type of transformation, right? And that transformation is the function. So this is the f. This is the function. This is the part that maps 1s to 3s, and etc. Now, for this section, we're going to introduce an entire new function, okay? A function that you have not been exposed to so far. So let me kind of get rid of this f of x notation, and let's introduce an entire new function. All right. So first, we're gonna before we get into this new function, what we call a vector valued function, let's make sure we understand, or just really quickly, just parametric descriptions. So in previous courses, when you were using parametric equations, even in previous videos here, you would have seen it written something like x equals some function of t, and y equals some function of t. And if we're in space, in 3 dimensions, we would have something like z is equal to some function of t. And it's simple as that. The t variable is what we refer to as a parameter, and that t variable is the one variable that that all of these functions have in common. It's as simple, I could capture that idea quite simply. If you were to, and I'll do this very quickly. If you were to throw a baseball, right? Now, let's think about how you could model that. Well, if you were stuck in XY rectangular coordinate systems, then to model the trajectory of that baseball, you would be somewhat stuck, right? Because you could model the horizontal distance and the vertical distance, but you would never know, for example, you would know at this particular point right here, you would know the horizontal distance and the vertical distance of that baseball, but you wouldn't know how much time it took to get there, right? And furthermore, if you decided to use time, well, then you might know at what time it had this particular vertical distance, but you wouldn't have the horizontal distance, right? Do you see do you see the limitation? If you want both, if you want to model something, right? If you want to be able to say at 3 seconds, this baseball was, 20 feet from the starting point and 10 feet in the air, right? If you want all three of those variables, time, horizontal distance, vertical distance, then you can't use the rectangular coordinate system because you're limited. That's why we use parametric descriptions, because parametric descriptions, I can find the horizontal distance, the vertical distance at a certain time. All right, now, so now that we know, you know what I'm talking about when I say parametric descriptions, the new function that we're going to be dealing with, let me write it first. We refer to this as a vector valued function. And just to make sure you understand what's happening here is, well, first structurally, let's just take a look at let's look at this function. So clearly this is a vector, right? I mean, you can see the I, J, K notation. So we are dealing with a vector. But notice that the components of the vector are itself functions. So the I component here is a function of time, if you'd like. The J component is a function of time, and so is the K is a function of time. So what is a vector valued function? Well, again, structurally, back to our set notations here, your input would be some parameter t. I like to use time because it does make sense when we're thinking about problems of motion. But hold on for a second. So if I could plug in maybe one second, if you'd like, if t is equal to 1. But what is actually the output? Well, the output is a vector. I'll say this one more time. So let me be real informal, and then I'll try to formalize it. So if you input a time, you will get an output of a vector. Or if you input some type of parameter, the output is a vector. The key part is what you get back out is a vector. The range is vectors. Everything that lives in this set, these are all vectors. All right, so now let's look at this a little bit more formally. So let's start with, we're going to read the definition of this vector valued function. First, let's just take a look at the notation. So here's a vector valued function if we're in just a plane. If we're in a space, then here's the vector valued function. And now let me read. So is a vector valued function where the components functions f, g, and h are real valued functions. Now, to make sure you understand this, what that part means, let me actually highlight what that means. F, g, and h are real valued functions. What I'm saying here is this f of t itself is the same real valued functions that you have seen in previous classes, like f of x. So these are just the normal functions that you're used to, f, g, h. And of course, instead of being a function of x, they're just a function of the parameter t. The r of t is the new type, our new function, the vector function, in which your output itself will be a vector. All right, I hope that makes sense. Your components, these are just normal functions. Input, the output is just going to be a real number, but the output of r itself is going to be a vector. Okay, so again, just different notation that we could use when representing the vector valued function. Let's start to build a little bit. So let's imagine for a second that take a look at this curve C. All right. No proofs, none of that stuff. I'm not doing that to you right now. I want your attention because we're going to talk about vector valued functions so much that I really just, all I want you to know right now is I want you to have a good idea, a good picture, geometric picture in your head of what's happening. So here's some curve C, right? For context, let's just say it's, I don't know, it's a meteor or a, some type of satellite or star, planet, or something. Whatever it is, this is something you're interested in modeling, right? You'd like to model this. So C is just some curve. All right, now in this little picture, O is just the origin. And now let's take a look at point P. So, in other words, there is some, there was or is going to be some time at which this meteor is going to be at this location. If you knew that time, if you knew T, then if you were to plug in, right, so R of T, let me go ahead and write my R of T. All right, so let's imagine. So this vector valued function is actually going to trace or model the trajectory of this meteor, okay? But how does it do it? Right? So let's assume that you knew the time at which this meteor would be at this location. Well, if you were to plug that t value into your vector valued function, you would end up plugging t in for each component. After you have evaluated the function, what you would have is a vector. And what would that vector look like? Well, that vector would point exactly to where that meteor is at that particular point. So can you imagine as it moves, as time goes by, you're just simply changing the vector that plots that trajectory. So that's the idea. So that's the idea. Now we're gonna come back to this exact picture, and when we try to understand the derivatives of these vector valued functions. But I hope that makes sense. That's really what's happening here is you're just producing vectors that are you can use to sketch a curve. All right, so let's jump into we need to jump into some actual practice. So the first thing I need you to understand is the ideas, the difference between a graph and a curve. I'll see if I can, let me see if I can demonstrate that to you. So watch, I'm gonna draw the same circle. All right, let's just assume that these are identical circles. Right? Now, we would say that these are the, I understand that I didn't connect them all the way, but we would say that these are the same graph. But we would not say that these are the same curve. Because when I started to draw this circle, the direction, the orientation at which it was this way. Whereas when I drew the second circle, the orientation was the opposite way. So a curve has orientation, and the orientation matters. So just because it's the same graph doesn't mean we say it's the same curve. All right, so take a look at what we have here. Now, it appears that we have t sub 0, t sub 1, t sub 2. So if I plug in t sub 0, the vector maps to this point on that curve. If I plug in t sub 1, a vector maps to this point on the curve, and so forth. Now, if I were the customer and you were to provide me this product, right? This is what I paid you to provide me. Well, if you left out this arrow marking, then it would be hard for me to know if this particle is moving this direction or if this particle is moving this direction. So the orientation matters, and we have to, when we draw our curves, we have to put our arrow markers so that we know the direction that, let's say, our particle is moving. And you can see the same thing here, right? You can see the orientation markings. Now, the next thing I want to do is the part, in my opinion, that students have the most trouble with, and that is thinking about the domain, right? The domain of these vector valued functions. So let's take a look at the following function. So r of t is equal to ln t I plus the square root of 1 minus tj plus tk. And the question that's in front of us is, what is the domain of t? So are there any restrictions? Can we plug in any real number that we want in for t, or are there actual restrictions to the domain? All right, and I think the best way, let me see if I can find myself a little bit of space. Yeah, I'm going to actually work up here. Here's the best way that I can explain to you how to find the domain. Okay? So what we're going to do is, unless we're told otherwise, the domain is assumed to be the intersection of the components. And let me show you the geometry of what I just said. So unless we're told otherwise, and unless we're told t is between 0 and 1, all right? That would be explicit, the domain would be explicitly defined. But unless we're told otherwise, it's assumed, it's implied, that the domain is simply the intersection of the components. And let's make sure we understand what that means. So intersection, so let's look at each component. So let's start with the first component, ln of t. All right, let's think about, I'll do this, I'll show you couple of different ways of thinking about this. So let's start with ln of t, and the first question is, what is the domain? What is the domain of ln of t? Well, if you just don't have that readily available, ln, or any logarithm function, the domain is going to be from 0, not including 0, to infinity. All right, if you don't believe me, you can try it. Take 0, plug it in to your calculator, ln of 0, and your calculator should give you an error message. It makes sense. ln of 0 equals some exponent, right? Y. But the reason why your calculator is telling you it's an error is because if you think about it in terms of exponential functions, that would mean e to the power of y equals 0. Do you understand that there is no way for me to plug in a y to make e to the power of y equals 0? That makes no sense. It's nonsensical, right? E to the power of 0 is just 1. There's no way to make this equation equal 0. So that's why the domain is from 0 to infinity. All right, let's look at the next function. So the next function is the square root of 1 minus t. And now let's ask the exact same question. What is the domain of the square root of 1 minus t? Well, this should be old hat for you guys. It's you know that 1 minus t, that radicand, has to be, it's okay to take the square root of 0, you just can't take the square root of a negative number, so it has to be greater than or equal to 0. So that ends up being solving for t. T has to be less than or equal to 1. So let's write that in interval notation. So that would mean the domain is from negative infinity all the way to 1 and including 1. Finally, the last component is just t, and there are no domain restrictions for t, so the domain would be from negative infinity to positive infinity. All right, now, but this doesn't quite answer our question, right? We weren't asked what's the domain of each component. We were asked what's the domain of the entire function. So it's a good place to start, exactly the way I started, and then until you just get good at this, I'll show you a trick that you can do. So I'm just gonna plot each of these domains. All right, I'll only do this one time, but just so you have it in your arsenal. So let's start. If I were going to plot negative infinity to infinity, this is just everything here. All right, and we'll say this is 0, 0, 0. All right, if I want to go from 1 to negative infinity, so if this is 1, we would have all of this. And finally, if I want from 0, I'm going to go ahead and put from 0 to positive infinity. And now, the reason why I take a second to show you this is if you imagine the intersection of these three graphs, right? What do they have in common? Well, in other words, we can, so in other words, if I just draw a line down here, wouldn't you agree with me that what's between these lines is the numbers that each graph has in common, right? I hope that makes sense. I mean, if I chose a number out here, that number would be in the domain of ln of t, and it would be in the domain of t, but it would not be in the domain of the square root of 1 minus t. So now let me go back and read what I said or state what I said just a second ago. So unless told otherwise, the domain of your vector valued function is assumed to be the intersection, right? That's what I mean by intersection, of the components. So in this case, I hope that it makes sense to everyone in the class that the domain for this function is going to be from 0 to 1. Any number in this set would be on all three of these graphs. If you chose a number outside of that set, then it wouldn't be on all three graphs. All right, so now where do we go from here? So the next couple questions I'm not as interested in as the remaining questions. So the next couple questions are all about sketching a plane curve. I'm not going to have you sketch in this class. I won't actually have you draw a graph. But so if I were to throw a question at you like this on a test, it would be a multiple choice question in which I provide, 4 or 5 different graphs like this, and then you choose the correct one. Right? So I'm not interested in the actual plotting of the plane curve. It's beneficial, but let's you and I be honest. We would use technology to do the majority of this plotting. So we don't want to spend a lot of time. We don't want to spend a lot of time doing antique methods here. So let me actually at least do this though. So the question reads, sketch the plane curve represented by the following vector valued function. So r of t is equal to the following. Now, notice that with this example, we don't have to worry about finding the domain of the intersections, right? Because we are already told the domain is between 0 and 2 pi. So that's important. 0 and 2 pi is our domain. Now, what I want to do for you is let's just imagine that you had a question on the test where you had to choose between 5 different graphs. Well, one thing that you could do is you could pick different points for t and plug it in, right? Like you could choose 0, pi over 4, pi over 2, and then you could connect your dots to form your curve, right? You would start at 0, you would stop at 2 pi. I'm going to show you another method that you can use, because your training, all of your training is in the rectangular coordinate system. So what I'm going to do is I'm going to get this back to an equation dealing with x and y. And maybe that alone would be enough for you to know what type of geometry you should be looking for. But let me go ahead and start now. So let me write the function. R of t is equal to 2 cosine of t I minus 3 sine of t j. And the way we're going to do this is let's go ahead and acknowledge that the x component, that is the horizontal component attached to I, instead of having an x, we have 2 cosine of t. So that means that we can set our equation x to be equal to 2 cosine of t. Likewise, where we would have had a y attached to that j component, we instead have a negative 3 sine of t. So let's just form an equation. Y, in this case, is equal to negative 3 sine of t. All right. If you want to get back to a rectangular equation, then we need to get rid of this parameter. That's the goal. All right? So let's go ahead and we're going to go ahead and divide both sides of this x equation by 2. And we're going to divide both sides of this y equation by negative 3. And now let's go ahead and write this result. So we have cosine of t is equal to x over 2, and sine of t is equal to y over negative 3. All right, this little trick is that we're going to make use of the identity, the Pythagorean identity, cosine squared plus sine squared is equal to 1. And you just be ready for this, because if you're gonna go through and try to convert these equations, you're going to use this identity a lot, right? It's a powerful tool for doing this. All right, so let me go ahead and show you what's going to happen now. So cosine squared of t plus sine squared of t we know is equal to 1. And quite simply, we know what cosine of t is, so we're going to substitute. And we know what sine of t is, so we're going to substitute. The result is x over 2 squared plus y over negative 3 squared equals 1. So I'm going to go ahead and just square this out, and then I'm going to throw the question that I'm going to throw at you is, can you look at this equation and tell the type of geometry that you're looking at? Well, that is the equation of what? It's an equation of an ellipse. And of course, we see the ellipse being drawn. So, okay, so at this stage, the only thing that you would have to be careful with, again, I'm just trying to think about if you're taking a test. How are you going to figure out the orientation? Let's assume that choice A looks like exactly what I have here. And that's the correct answer. But there's another choice B that looks identical, except the orientation looks like this, right? It's opposite orientation. So now the last question that I have for you is, what is going to be your strategy for finding the orientation? Well, you could try to find the orientation. Well, it's going to be better to go back to the original vector valued function in order to think about the orientation that way, because we know that t starts at 0 and then proceeds to 2 pi. So that's kind of what you're seeing here. It starts at 0. So 0 maps to, let's say 0 maps to here. Now if you were to plug in the next t-value, and that maps to here, that alone tells you the direction, right? The idea that the first t-value was here and the second t-value was here tells me the direction that we're moving. So one more time, you might have to just go back and plug in some t-values so you know the direction, the orientation of your curve. But that is all that I want to do. All right, let's go ahead and take a break, and when we get back, we'll finish this section.